Let's continue looking at this relationship between the spatial domain and the frequency domain. Here are some simple properties of the Fourier transform. We started with one that we already talked about. Everything is linear because we're just doing sums and multiplies. All right. The one we just described was this convolution one, that convolution in the spatial domain is multiplication in the frequency domain, and vice versa. One that's kind of interesting is scaling. So if I scale a function by a constant a, so let's think about it this way. Suppose a was greater than 1. Let's suppose a was 2. All right? Well, that would mean that when x had been 1, now x is 2, so it would shrink, right? When you multiply by a number bigger than 1, right? So if I had some function, right, now what happens is this value gets moved over there, so I essentially shrink that function, okay? So when I shrink a function, things are going to now wiggle faster, right? Because they were wiggling slower before. If I pull it in, it now wiggles faster. And so what happens is I end up stretching the Fourier transform. And this is the formula for it, 1 over a times f of u over a. So it's got that inverse property, which is just like that Gaussian idea also, right? If I make it fatter, my Fourier transform gets skinnier. One last one to look at, and we're not going to use this much, but I wanted you to see this, is when you take the derivative of a function, so this is some nth derivative, you multiply its Fourier transform by a function that's proportional to the frequency. So suppose n was just 1, you're taking the first derivatives, right? What that says is that you would be multiplying f of u times u, which means the higher frequencies get accentuated, which was exactly what we saw when we took derivatives. Remember when we added noise, high frequency noise, and then we took the derivative, the whole thing blew up? That's because you were multiplying it by, when you take this derivative, you multiply the high frequency components.